All right, welcome back, everybody. Class recording has started. So, on Friday, we started in on the electricity and magnetism section, which is Unit 5 of your book, and we had just gotten to here where we started talking about a circuit, right? And so, a couple of rules apply when we do a circuit, right? First, it's got to be a complete path of conductors to get from one side of the cell to the other side of the cell. And, oh no, come on. Come back to me, pen. There we go. So basically we talked about getting from an area of high potential energy to an area of low potential energy. That's the potential difference thing and all that stuff, right? So this first one, this circuit contains two components. It contains a light bulb, and then it contains a variable resistor. And like its name suggests, right, we can vary the resistance on it. Decreasing the resistance increases the current. Increasing the resistance decreases the current. And whenever we're analyzing a circuit, right, we're going to basically use Ohm's law, which can be rearranged into this equation or into this form, showing the relationship between voltage, current, and resistance, or potential difference, current, and resistance. Okay? Good there? So the first part said, on the circuit above, add circuit symbols showing the correct positions of an ideal ammeter and an ideal voltmeter. Ammeter measures current, just like amps, right? That's the unit the current is measured in. So we always measure current in series. So in this case here, the ammeter needs to be part of the circuit, and that's why I drew it in that spot right there. A voltmeter measures potential difference, right? So it looks at the energy of charges at one point versus another point. In this case, that would allow the voltage current characteristics of this lamp to be measured. Voltage, or potential difference, needs to be measured in parallel, right? So we have to take a reading, basically, of the energy of these charges before they go into the light bulb, and then after they go through the light bulb, right?
If there were like multiple lamps, like parallel,
Yeah. In that case, you would have to measure the potential difference of each lamp individually, right? Or we had something like this. Okay, so there's two lamps in parallel, right? If we wanted to measure the potential difference across the whole circuit, we'd go like here. Does that make sense? Right, before it splits apart into different sections. But then also too, in this case, we're also just measuring the potential difference across the battery then as well, which is, so the potential difference across the battery should be equal to the potential difference across the whole circuit, right? Because whatever energy the charges gain going through the cell, they have to turn into something else in the course of the circuit. Right? So here, it would depend on what we were trying to measure. If we wanted to measure the current through a light bulb, we'd have to put it there, or say again?
either side.
Yeah, as long as it's in series, it doesn't matter. Okay? Like for the second light bulb, we could also put it like right here. Those two ammeters should measure the same thing because it's part of the series circuit that is that second light bulb. If you want to measure individually, yes. But what we find with the parallel circuit is if we put an ammeter there, orange and red would have two different readings. Orange is going to be faster. Orange is actually going to be the sum of the reds because all of the current coming through here has to be divided between these two things, right? This gets into, here, we'll pull it up right now. This is a good example of, let me see if this is it. No. That gets into actual numbers. These are, here we are. these examples that we just talked here are examples of Kirchhoff's laws, which which we use, there we are, which we use to analyze circuits. And there are basically two of Kirchhoff's laws. They're down here. His first law says sigma I equals 0 if we're talking about a junction. Second law, sigma V equals 0 if we're talking about a loop. Okay? So let me go back to where I can write, and we'll talk about this. So Kirchhoff's laws. Number one, sigma I equals 0 for any junction. Okay? This is a junction right here, a spot where we're splitting current, basically, right? So in this case here, let's get rid of, yes, because, remember though, whenever we do sigma, we got to take into account positives and negatives, right? So if we talk about this junction right here, orange would have a positive value because it's going into that junction, but then red would have negative values because they're coming out of that junction. Does that make sense? True, but when we're talking about, like I said, this number, Kirchhoff's first law relates to any junction in the circuit, not for the.
Two or more. 3 or more.
Yes.
Okay.
Yeah. No, two or more. Because technically, like, we could say that this is a junction right here, and then in this case, orange is positive to that junction, red is negative to that junction, so we'd have
in relation to the point.
to the point. Yeah, this only applies at any particular point, not for the circuit as a whole. All right? So yeah, in this case here, right, let me use some highlighters. For this example, that when we look at Kirchhoff's laws for a current, we basically look at it at one point in that circuit, not for the circuit as a whole, but for one point in that circuit, okay? But then Kirchhoff's second law says the total potential drop has to be equal to 0, but in this case we talk about a loop, okay? So in this case, now we have to look for a complete conductive path. In this case here, let's just draw on this one, right? Here, charges gain potential energy going through the cell, but then lose potential energy going through the lamp. However much they gain through the cell has to equal however much they lose through the lamp. Okay?
I have a question about the first one. Okay.
Good.
It's positive to a junction?
Yeah, something
Negative
coming in
from?
would be positive, something coming out of that junction would be negative, right? And I mean, technically we could say it the other way around if you want to, but you know, because we're still going to end up with 0 in that case, right? Whether we call orange positive and red negative, or whether we call orange negative and red positive, we're still going to end up with 0 in that case. But it makes most sense if you think about positive current flowing into that junction, negative current flowing out of that junction. So, yeah, are we good with Kirchhoff's laws, right? And that is important when we're analyzing that circuit, right? To know that current flowing into one spot has to be equal to current flowing out of that spot, and then vice versa, not vice versa. Voltage, we have to look at an entire loop and look at how much does the potential energy gain and how much does the potential energy drop over that course of that loop. All right, good there? So, getting into that, for part B, it says explain why the potential difference across the lamp cannot be increased to 12 volts or cannot be reduced to 0. All right? So, if we talk about Kirchhoff's second law, looking at a loop, right, and in this case, a series circuit is just one single loop, right? The potential difference increase has to be equal to the potential difference decrease. The battery increases potential energy. It's what it does, so it's a positive potential difference. But then the lamp or other parts of the circuit will decrease the potential difference. If the potential difference increases by 12 volts going through the battery, we can never get 12 volts out of the lamp because internal resistance, right? The wires have some resistance. This variable resistor, we can't make it zero, right? It's variable, but it's not perfect. It has some kind of resistance, and as a result, somewhere along the way, we are going to lose some of that potential energy just by making the charges go through the circuit, so we're never going to get everything out at the lamp that we put into it at the battery. Okay, is that good? And then, cannot be reduced to zero. There's one way to make the potential difference across something zero. Bypass it. Yes, that's one action. I think you're on. Say again. Well, a short circuit is one way to do it, but a short circuit results in what current through the rest of the circuit? No. Well, through the short circuit part, the current is super high. But what's the current in other parts? Zero. Potential difference is zero if there is no current. Okay? Can this circuit, as it's constructed, ever have zero current? It can't. This variable resistor, regardless of how high we can make it, we can never take its resistance to infinity. Does that make sense? That's what we would need to completely stop the current. Say again? No, not with the resistor. But you know what you can do it with? A switch, right? If we break the conductive path, then there's no current.
So even if you have like a super high ohm resistor,
I mean,
theoretically, something's going to do.
Effectively, can you do it? Sure. Theoretically, can you do it? No.
Okay.
Does that make sense?
Yeah.
You know, like if you have so much resistance in that variable resistor that basically you're taking these charges through the lamp super slow, you're just not going to see any light out of that lamp because it's not it's not transferring enough electrical potential energy into light for you to notice it. You know what I'm saying? So effectively, we've reduced the current to zero, but not in reality.
There's like a Zeno's paradox joke about that. Like, you know what Zeno's paradox is?
No.
Anyone? It's like, there's a line, right? And Zeno says, you can get to the end of the line, you have to go halfway before you can get there.
Right.
So there's a nihilist, a nihilist, a mathematician, and an engineer. The nihilist says, like there's a hamburger, right? The nihilist says, I don't care, I'm not going to do this. The mathematician says, I'll never get there because I have to go halfway each time. And the engineer says, I can get close enough to eat the hamburger.
Yes.
So,
Yeah. Like, that's sort of the same. That's sort of the same thing as a limit, right? Like a limit in math class, you never are actually going to reach, or an asymptote, I guess if we talk about it that way, right? You can get really close, but you can't ever get to that limit. Like here, effectively, we could probably get to a point where we have effectively stopped the charge flow, but in reality, we can't. The only way we could do this is put a break in the circuit, and that doesn't exist in this circuit as drawn. Okay? So that's why we can't get that potential difference down to zero, because because current is always going to be flowing. So, all right. Yeah, that's what it is. All right. So the next thing on the list gets a little bit tricky. All right. We can determine, or we can affect the amount of current flow through this circuit by changing the resistance of this circuit. We can increase the current flow by decreasing this resistance, or vice versa. All right? But, like we said, we can never effectively stop it, or sorry, we can never theoretically stop it. But there are some things that allow us to stop it, and one of those things is a potential divider. I'm going to pull up this thing right here because it does a better job of explaining it. So,
Is it a component?
yes, it's a component. So basically what it does, like it says here, so a potential divider is also called a potentiometer. Okay? So we're talking about basically changing how much current we have flowing through different parts of the circuit. I'm not real familiar with the potentiometer, I'm not going to lie, but reading up on it a little bit, it looks kind of like a switch. So we can effectively cause current to flow in one direction versus, or in one part of the circuit versus another part of the circuit.
So it's a transistor.
As much as I can tell, yes. Although a transistor, I think, transistor allows charge to flow in one direction and one direction only. This is a little different. Like we can sort of determine which way we want it to flow. Almost like a, and I'm totally thinking off the top of my head here, kind of like that, a switch in a rail yard that allows the, is the train going on this track or is it going on this track? Well, we need to flip the switch to go this way or that way.
So do you supply a voltage to it?
Yep. So that goes here, like the voltage source is attached to it, but then you can adjust it to then allow the voltage source to flow through like here to another component. But you can also prevent current from flowing that section and just flow through here. Okay. So that's the potential divider allows then for different things, all right? So here is, so do they have our two circuits? Okay. So I don't have the total volume of it, but you can kind of see where it goes. Okay. This one at the top, the variable resistor, this is exactly the circuit that we've been dealing with, right? They're in a different order, but it's the same thing, right? There's the ammeter measured in series, there's the voltmeter measured in parallel, the R is a resistor, it was a light bulb in our circuit, whatever, okay? Here is, can you guys, consider this just to be connected, all right? Is that, there's just a wire along the bottom there. So with the potentiometer, we said, in circuit A, the one with the variable resistor, we said we could never prevent current from flowing through that resistor. Here we can. By adjusting the potentiometer, you can just allow current to flow through this loop of the circuit, and it never gets over here. And if it never gets over here, this is 0 and this is 0. Okay? So the question says, draw a circuit that uses a potential divider to enable the VI characteristics of the filament to be found. So instead of using this variable resistor, we put in the potentiometer. And so the picture looks exactly like we just had. Voltage source. And then this is our potentiometer or potential divider. Potentiometer. Okay. Okay. And for part CII, explain why this circuit enables the potential difference across the lamp to be reduced to 0 volts. We talked about that the, say again? You cut off the current, right? That's really the only way that you can make the potential difference 0 across a component is if there's no current flowing through it. And the only way you can cut the current off is if you don't allow the current to flow through that part of the circuit. So the potential divider, or the potentiometer, just allows the current to flow through this portion of the circuit, and it never gets over there. Right?
Are there any like other parts in that access to this potentiometer?
So with this one, so Yusuf, let's go back here to this picture. Okay. Here we end up, these are just different types of circuits that have different types of resistors on them, right? Really what we're doing is we're controlling the flow of current through different parts of the circuit, right? So here, in this circuit, LDR, light-dependent resistor, right? When light shines on the LDR, there will be a decrease in potential difference across the LDR, okay? So, when there will be a decrease in potential difference, that means the current slows down, right? So in this case, when light hits it, the light-dependent resistor is a device whose resistance depends on the amount of light shining on its surface. An increase in light causes a decrease in resistance, right? So, when light isn't shining on it, it has a high resistance, which stops the flow of current, or slows the flow of current to this resistor. Does that make sense? The 10 kilo ohm one, all right? So there's a large resistance is a big potential difference, which means there's not much potential difference going on here, okay? A small resistance means that more potential difference has to occur here. Remember, whatever energy they pick up through the battery has to somehow, some way get turned into other stuff. When there's no light, this light-dependent resistor turns a lot of that potential difference into probably heat. It's just a resistor that's really high, right? And then there's not much here. Sorry. This is a night light that turns on in the dark and automatically turns off when the light goes on. Does that make sense? When the room is dark, resistance is high here. This light bulb doesn't work because not enough current flows through it. Does that make sense? When light goes on, right? Sorry, other way around. When light goes on, flip it around. When the light goes on, there's a lot of resistance. You can go either way. Either light is a big resistance or light is a small resistance, right? When light goes on, this resistance increases and this goes off. When the light goes off, this resistance decreases and this goes on because there's more current that's flowing through it. Does that make sense? Technically, the charges are going to come out of here and flow this way. Conventional current would flow that way. But either way, because these are in series, if you stop current flow here, it stops there too, right? Because series, everything in series has the same current, right?
It's kind of backward.
What?
I feel like shine a light on it, it would increase resistance. Like that's
You can go either way. Like there's different things that work different ways, right? You know. So I'm trying to think of why that would be. Can't think of it off the top of my head, but so yeah, I mean, and different things act different ways, right? Sometimes we want things to be on in the light, and we don't want them to be on in the dark, and vice versa. So depending on that. Down at the bottom, right? This this, a thermistor is a heat-dependent resistor, right? This is basically a thermostat, sorry, an electronic thermostat in your house, right? Depending on the temperature, this allows more current to flow through other parts of the circuit and other parts of the circuit, right? So that when the temperature changes in your house, that changes the flow of current through different parts of this circuit, which can turn on your heating system or turn off your heating system.
Just do it digitally now.
Say again?
Do they do it digitally?
Well, this is hooked up to a digital sensor, and so you're basically measuring the temperature based on what resistance this.
Oh, so it's variable? It's not just off on?
No, it's variable, right? Well, sorry. It's variable on the resistance based on the temperature,
Okay.
right? So if we were to measure the temperature and the resistance, that would change.
The resistance go up or down?
So
Oh, wait, no, that makes sense.
when the temperature of the thermistor increases, there will be a decrease in potential difference. That means less current, all right? Say again?
Higher resistance.
Higher resistance, yeah, right?
So that one makes sense.
So, but then what we do with the electronic thermostat is the electronic thermostat can be programmed to turn on or off the system depending on how much current flows through here, because the amount of current depends on the temperature. And so you can change it to say, okay, when the current hits this, when the temperature, you can change the thermostat to say, when the current reaches this much, I want my heater to go on. The current that's going through relates to the temperature. So basically you're changing it based on the temperature. Does that make sense? So those are the two other types of variable resistor circuits that they talked about in the book. So yeah, yes. Which kind of makes sense, because if you think about it, right, as the heat goes up, what do the particles do more? They move, right? And that includes the so those charges have a harder time getting through there because everything's moving more, right? So that hopefully conceptually makes sense. Is that good? All right. Okay, we did that, right? Explain why this circuit enables the potential difference across the lamp to be reduced to 0 volts, because we can effectively just have current flowing through this portion of the circuit. No current gets over here, no potential difference over there.
I was thinking about the light dependent one and thermistor switches that were dependent on light.
Not exactly, but they're kind. Say again. It's really, again, it's just changing. Here, let's go back to make sure that I'm stating it properly, right? Okay. When light shines on the LDR, there will be a decrease in potential difference across the LDR, and that means that, yeah, decrease in resistance. Light shines, there's a decrease in PD. That's an increase in resistance.
Okay.
Yeah, that makes sense, right? So yeah, when the light is on, or when it's light in the room, it's blocking current flow, right? But when the light goes off, then we go, right? Okay. Good there? All right. And so, all right. So the graph below, this is a different question. Well, this does not relate to the lamps that were in the previous question. I really wish they would have made this a completely new question, but they just made it part D of question 3 or whatever we're on, so. Well, this one's got, yeah, this one's got A, and then it's got BI and B1 and B2, and then it has C1 and C2, and then this is D, but it's not related to that circuit we were just talking about. It's a total different. Yeah, it's not done either. So okay. Yeah. So all right. So it says the graph below shows the current voltage characteristics for two 12-volt filament lamps A and B. All right. State and explain which lamp has the greater power dissipation for a potential difference of 12 volts. All right, so that's what lamps do. Lamps power dissipate, because power is how much energy we're converting per second, right? There is a way you can do this. I won't show it to you right now because the formula will be on your sheet, but we can calculate the power dissipation if we know the voltage and we know the current. Okay? So power is equal to voltage times current. Okay? In this case, it's going to be lamp B, right? Because we know the voltage for both of these lamps is what? 12 volts, right? They're both on that same level. But lamp B has more current, right? So its power dissipation is going to be greater, right? This is, it dissipates more power per second. If we're talking about a light bulb, this is a higher wattage light bulb, right? Higher wattage light bulbs look like what? They're brighter because they're converting more potential energy from the voltage source into light energy at the lamp, right? So yeah, in essence, this lamp B is a higher wattage light bulb than lamp A is, okay? Good there, right? So for 3 points, right, lamp B is 1 point, right? 2 points would be they have the same voltage but different current, right? And that leads to greater, yeah, this would be a point. The formula would be a point, and then explain it there. All right, we'll continue on with this tomorrow. We'll get there.